So we are dealing with question number 11. Light from a discharge tube containing hydrogen atoms falls on the surface of a piece of sodium. The kinetic energy of the fastest photoelectrons emitted from sodium is 0.73 electron volt. The work function for sodium is 1.82 electron volt. Find A part, the energy of the photons causing the photoelectric emission. B, the quantum numbers of the two levels involved in the emission of these photons. C part, the change in the angular momentum of the electron in the hydrogen atom in the above transition. And the last part, the recoil speed of the emitting atom, assuming it to be at rest before the transition. So if we begin solving this particular problem, so we are saying the energy of photon causing photoelectric emission can be written as, so the energy of photon causing photoelectric emission can be written as the sum of work function for sodium metal plus the kinetic energy of the fastest moving electron, which I am referring as kinetic energy maximum. So over here I can put these values as the kinetic energy of the fastest moving electron is 0.73 electron volt, and that of work function is 1.82 electron volt. So on adding them we get a value equivalent to 2.55 electron volt. So this is the value of the energy of photons causing the photoelectric emission. So with this we have ended up part A. So now the next one is asking the quantum numbers of the two levels involved in the emission of these photons. So we begin by writing this formulation that for the hydrogen atom we know that the value of total energy can be written as minus 13.6 z square by n square. Now since a hydrogen atom is involved, so we write it as minus 13.6 by n square. Now let the electron jump from n2 to n1. So if the electron is jumping from n2 to n1, so we can write the energy corresponding to En2 minus En1, and the value can be written as minus 13.6 by n2 square minus of minus 13.6 by n1 square. So from here we obtain the expression as the value of the energy change involved is 2.55 electron volt, which we have calculated in the first part, and this can be equated to 13.6 1 by n1 square minus 1 by n2 square. So this is the required equation, which I am referring it as equation 2. This was equation number 1 for this problem. So now if we solve this problem, so for the value of n1 and n2, we solve using hit and trial method. That is, n1 and n2 are integral values. So if we solve by hit and trial method, the value we obtain over here is n2 is equal to 4 and n1 is equal to 2. So it is obtained by hit and trial method. Kindly keep this in mind. We will not be able to frame any other equation for this particular part. So it is obtained using hit and trial method. Kindly keep this in mind. We only know that the value of n1 and n2 are integral. So using this parameter, we solve this particular equation using hit and trial method, and we obtain this value. Now the next part, the question is asking us the change in angular momentum of the electron in the hydrogen atom in the above transition. So the value of angular momentum, so we say angular momentum mvr is equal to nh upon 2 pi. That is, we say that angular momentum is quantized. So using this working formula, I can calculate that the change in angular momentum, we are referring it as n, can be written as n1h upon 2 pi minus n2h upon 2 pi. So if we do this, we obtain from here h upon 2 pi 2 minus 4, and we write this value as minus h by pi. So if the magnitude is asked, we can say that the change in angular momentum is h by pi. The next one, the change in the angular momentum we have obtained. The recoil speed of the emitting atom, assuming it to be at rest before the transition. So we are solving the last part. So over here, the question is asking us to calculate the recoil speed of the emitting atom, assuming it to be at rest before the transition. So this time the momentum of the emitted photon will be calculated first. So let us begin by finding out the momentum of the emitted photon. So we begin by calculating lambda using the equation h by p. So from the Broglie equation we are calculating lambda as h by p, or from here I can say that p is equal to h by lambda, and I can write it as, that is, we can multiply by speed of light on both the side. So we obtain something like this, and then we can write it as E by C. So hc by lambda can be written as energy. So we write it as P is equal to h by C. So from here we can calculate P as the energy value was 2.55 multiply by 1.6 into 10 to the power minus 19, so that we can convert it in joule, divided by speed of light 3 into 10 to the power 8. So this is the value of the momentum of the emitted photon. Now the atom was initially at rest, so the recoil momentum of the atom will be same as the emitted photon. That is according to the conservation of momentum. So if m be the mass and v be the recoil velocity of the hydrogen atom, then we can say that by applying momentum conservation principle, that is P initial is equal to P final, I can say that the initial momentum of the system was equal to 0, and finally we have the momentum of the photon emitted. So emitted photon plus the momentum of hydrogen atom. So from here I can say that the magnitude of momentum of hydrogen atom is equal to the momentum of emitted photon. So if I use this expression, so I can write the momentum for hydrogen atom as mass into velocity, and we can equate it with the value of momentum which we obtained, that is 2.55 into 1.6 into 10 to the power minus 19 upon 3 into 10 to the power 8. So from here we can calculate the recoil velocity as 2.55 into 1.6 into 10 to the power minus 19, and the mass we are putting it as 1.67 into 10 to the power minus 27 multiply by 3 into 10 to the power 8. So from here we obtain the value of recoil velocity as 0.814 meter per second. So I can explain you it in this way, that initially the hydrogen atom was at rest. Now post this, the hydrogen atom will start moving in this direction, and the emitted photon will be emitted in this direction, such that the momentum is conserved between the hydrogen atom and the emitted photon.